Okay, so what should be? Did I get the wrong? Yeah, it shows the physics law. It's physics 11. Where is it now? Hmm. Okay, so what do you need to find the weight of an object? You should have already written that question down, so I'm just going to skip ahead. So this is the equation for weight. That's the force of gravity, or what we also call weight. This is just an abbreviation for 9.8, and the units are meters per second squared. And this is mass, and it is in kilograms. So make sure that you're careful with the units that are given as far as the mass. If you're giving grams, know how to convert. Okay, make sure you use kilograms when you do the calculation. And then the unit for the force or weight, force of gravity or weight, is newtons. Okay, 2. Describe the motion of a ball thrown upwards in terms of, I'll write it out for you in a second, in terms of its velocity, acceleration, and energy. Okay, so what I'm doing is I'm just covering what I think some of the finer points are that you need to be made aware of. So this is on top of the review package that you should have gone over, plus the tests. And again, anyone who didn't get their test, tests are there at the side. Motion of a ball thrown upwards. Going over in terms of velocity. Velocity implies that you have to include the direction as well. I didn't say speed. I said velocity for a reason because velocity is a vector. It's got a direction affiliated with it. So velocity, acceleration. Okay, so include the directions with these. And energy. Energy doesn't have a direction, but it does change as you go up and down. So we're looking at the different stages. So this ball's thrown up. It starts here. That's your initial. It's thrown upwards. You know from experience it's going to reach some peak, and then it starts to move down. Okay, so call that 2, call that 3, call that 4, call that, let's say it reaches, comes back or returns to its starting position. So I'll give you the answers in a second, but let's deal with velocity one at a time. Velocity first. So you write it down. What do you think's happening? I'm only interested, it's basically at this point in position number 1 left your hand. So you've accelerated it out of your hand. It's moving upwards. So here it's going to be at its maximum velocity. Leaving your hand at position 1, it's just left your hand. The maximum velocity is here. Okay, it's a positive velocity because it's moving upwards. We're defining positive to be up. Okay, I'm going to skip right to position 3. What's the velocity at position 3? It's turning point. Yeah, very good. Any turning point 0. So in between 1 and 3 at position 2, the velocity is less. We can't say it's exactly half. We could calculate it, but it's less. E is less. It's decreased. Less than position 1 is what I'm referring to. It's still positive because it's moving up. Okay. Position 4, it's moving down. Let's skip right to position 5 because then we can come back to 4 and describe it. 4 in terms of 5. So this is now at position 5 at a max, but it's negative. It's moving down towards the ground. Okay. Position 4, go back to 4. It's somewhere in between 0 and its maximum. So it's increasing. It's increased at this point. Alex is on. That's funny. Okay. And it's still negative. And when I say increased, I'm referring to position 3, right? It's increased from 0, some negative value. Increasing in value as it goes from 0 to 4 to 5, but negative. Okay, so what about the acceleration at any point? At 1, 2, 3, 4, 5. Remember, it's moving freely, only under the constraint or pull of gravity. Does the acceleration change? Is it a different force on the way down than it is on the way up? No, it's the same pull of gravity. It's always acting down. That's why the acceleration due to gravity is the same. Whether it's going up or down, it's negative 9.8. I just put, you can say 9.81, but I'll just keep it short, 9.8. Negative 9.8 on the way up or down. Referring to the fact that the pull of gravity is always the same, whether it's going up or down. It's always pulling towards the earth, and it's the same value, whether the ball's moving towards position 3 at the top or moving down back towards the ground. Constant value, it's constant. It's constant. Okay, energy. I'm going to make a copy of this so I can just refer to energy. Oops. Okay, well, now express what's different about the different positions in terms of energy. You could talk about maximum and minimum. Points where one of the energies is 0. Okay, so it's left your hand at position 1. So kinetic energy is at its max here. Why? Because that's where the velocity is at the max. At the very point where it's released your hand, it's going up. Let's skip right to position 3. You told me the V is 0, and that implies kinetic energy is 0. What about in between? Kinetic energy is at 50%. at position 2, somewhere in the middle. What can we say about if the kinetic energy is at the 50% mark, what's the potential energy? Yeah. There's always a trade-off. If you've lost some kinetic energy, you gain the same amount of potential. And at the very top, in terms of percentage, what can you say about? Yeah, 100% potential at the top. And then position 4, which is roughly the middle. 50% potential, yeah. Go 4. So you've lost some potential. You lost 50% of the original potential. Where did it go? Yeah, it turned into kinetic. What's your potential? If you're measuring, this is not quite ground level. Let's say you're measuring from this point here. You're measuring your potential from there. So your potential is what? The height is 0, so potential is? Yeah, potential always, this is a key important thing to remember. Potential always depends on height. So if height is 0, what does that imply? If h is 0, PE is 0. So the potential at position 5 is 0. What can you say in terms of percentage about the kinetic at position 5? It's 100%. Alex is in the way. Is there any way to... You can't... No, I don't want to remove him. I just want... Oh, that's it. That's better, eh? Okay. Okay, next. Next question 3. Draw free body diagrams. Yes, you're going to have to draw free body diagrams of objects moving at constant velocity or accelerating. And I looked at the exam. There is one question on elevators. So you're going to need to know how to go over the elevator problems in the review package I gave you on the front page of the second set of review. So okay, so draw free body the free body diagrams. For objects that move at constant velocity. Oh, that's an at. I'll just write at. Move at constant velocity. Or accelerate. And included with that sideways, we're going to deal with sideways motion, moving to the right, and then we'll deal with upwards motion. So both to the right okay, we'll deal with that first for constant velocity and acceleration, and then upwards. We'll just draw the free body diagram. Okay, so for sideways motion, for to the right, let's say moving to the right, at constant v with the constant velocity. Okay, why don't you do that? Draw it. That's a 2 there. Draw the diagram moving to the right. I'll just draw for you a little rectangle, but okay, now let's say it's moving to the right. What's the diagram for it? Just represent that little box, whatever it is, with a dot. What are the forces acting on it? To move at constant velocity. Let's say there's friction. There's friction. So I'll include that in it. What do you need to keep it moving at constant velocity? I'm not finished. Yeah. You need something acting to the right. Otherwise it'll slow down. How do I draw this? How does it compare to the force of friction? Longer? If it's longer, it'll accelerate. Shorter? Equal. If it's shorter, it'll decelerate. Any other forces, since we're talking about moving along the ground, anything acting on it, which force is always in a free body diagram? Yeah, Toby? Yeah, we get to that. Normal force isn't always there, but gravity is always there. Fg is always in every diagram, regardless of whether it's moving sideways or upwards. And then that's how you get the normal force. That's why the normal force is there. It reacts against the weight. And yes, they're equal. Okay? Now next, accelerating to the right. Draw that. I'm going to make a copy of it because I'm going to do it real fast, save us a little time. But draw it. Not constant velocity, no longer constant velocity. It's accelerating. Is she right? Sure. Yes. The reason why something accelerates is because one force is larger than another, opposing it. Okay? If it was shorter, it would slow down. If it's the same, it's balancing the force of friction, just keeps moving with a constant speed. But if it's longer, that's when it starts to pick up speed. That's why your car accelerates onto the freeway. The force of the engine is stronger than the air resistance. Okay. Next, upwards motion. Constant velocity upwards. Draw free body diagram. Which force is always in the diagram, regardless of whether it's sideways or upwards? Yeah, good, Fg. And it's, if there was just force of gravity and the object was moving up, it would eventually, it's like throwing a ball up. If there was only Fg action, it would move up, reach some final height, and then start to move down again. But this is moving with a constant velocity. It's like an elevator moving upwards. The only way it can move upwards with a constant velocity is for there to be some sort of force pulling on it. So how do I make this force? Do I make it shorter? Equal? Longer? Equal, good, yeah. Has to be. Now sometimes you'll see it, I'm going to call it FA. Sometimes you'll see it written as this, FT. It's the same thing, tension in a cable. It's just an applied force. And yes, FA in magnitude is equal to FG. Okay, last one, accelerating upwards. Okay, now, when you go over that review sheet that I gave you, it was an older assignment on forces that I, again, put at the front of the second review sheet. Make sure you go over all of them, right? This is just the main typical problems you could be asked. There's some variations on this, but I gave you full solutions with that as well, including the diagrams. They're there. Accelerating upwards. Okay, I'm going to make a copy of this. I don't need to get rid of that. I need to get rid of this. How do I vary it? If it's this elevator, let's say, it's accelerating upwards. How does the FA compare to the weight? Longer. Yeah, if it's shorter, it eventually, if it's moving upwards, it's eventually going to slow down. If it's the same length, it'll just keep moving at constant speed, so it's got to be longer. FA is bigger than FG. Okay. Question 4. List all the vectors that we've covered or talked about. List all vectors that you know of. Displacement, sometimes you'll see it written like this. Same thing. That's distance with a direction. It can be negative. If you're moving to the right, it's positive. If you're moving up, it's positive. Down, negative. Velocity, which is based on displacement. Right? Velocity is this. It's displacement over time. So since velocity is based on displacement, it also is a vector. It can be positive or negative. If you're moving up, if the ball is moving up, it's positive. You throw the ball up, it's positive velocity. The moment it starts to move down, it's negative. Acceleration. Acceleration is based on velocity, on a change in velocity. So it also is a vector. Whatever you base on a vector is a vector in general. It can be positive or negative. If it's positive, it's speeding up. If it's negative, the object's doing what? You've got a negative velocity. Let's say the car's moving to the right, but you slam on the brake, and I said to you, it's now got a negative acceleration. What does that mean? Car's got a negative acceleration, slowing down. So it also is positive or negative. Positive, speeding up. Negative, slowing down. Okay, next, blah, 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 force. Force is a product of mass and acceleration. Acceleration is a vector, so is force. Any force, not just net force. Any force. Positive or negative. What else? Momentum. Momentum is, we'll talk more about this later. Change in momentum is force times time. So because momentum is a product of a vector, it also is a vector. Vector based on force. It's a product of force times time. Okay. Did we cover any more? No. Energy is not. Energy is what we call a scalar. Energy is a scalar. Energy, work, power. No direction to it. Scalars. Distance, time. Okay. 5. How does Newton's third law, write it down for you. How, in terms of forces, how does Newton's third law relate to collisions? Right? So two balls hit each other. So you got a ball here. You got a ball here. They hit. How do the forces compare? They're going to hit each other. But when they hit, boom. There's a force on, this is 1 and this is 2. There's a force on 1. How does the force on 2 compare? Yeah, opposite, but equal. During a collision, that's how we come up with the conservation of momentum. The forces acting on these two balls are F1 is opposite and equal to F2. Did I write it 6? I don't think I wrote 6. I called it 6 and then I skipped it. Okay. Call this 6. What does recoil mean? Just write it down. Don't tell me. And describe it in terms of velocity. The gun has a recoil. What does that mean? Should be there, Andrew. So you fire a bullet to the right, what happens to the gun? Yeah, it recoils. It pushes back in the opposite direction. Recoil, push back in the opposite direction. Okay. So the bullet moves this way. Whoa. And the gun, the legal gun, bullet goes that way. Gun goes that way. It's recoiled. It's moved in the opposite direction in response to some sort of explosion. It recoils. Has a negative velocity. That's the point. Main point is velocity. This is positive velocity. The gun's velocity is negative. Okay, next. How do you find the impulse of an object given not the force, but the velocity? Well, you should know how to calculate the impulse given the force, but the harder question is how can you find the impulse of an object given its velocities obviously the masses are given, they're almost always given. Given an object mass and velocities. And by plural, I mean, by velocities, I mean before and after, right? Before and after, it's given an impulse. So impulse is usually calculated by force times time. Let's say you're not given the force and time, you're given the mass and velocities. How are you going to calculate it? You should put this on your formula sheet. This force times time is the same thing as change in momentum. You're going to calculate it using the change in momentum. I would do this and go even further on your formula sheet. Include this, what change in momentum is. What is it? Final minus initial momentum. What is that? Yeah, I mean, I could write it out full. I'll do it in full. I don't want to write too much out. Right? That's what it means. Final minus initial. What's the equation for momentum? M times V. Yeah. Final minus initial. That's it. You can write that in your formula book. You could abbreviate it further if you want, but that's essentially it. That's, what is this? This is your final momentum. What's this? Initial momentum. That's another way of calculating impulse. Final minus initial momentum. This is an easy one. What do you need to calculate potential and kinetic energies? Just write it down. Yeah. Give me all the variables and corresponding units. I'll get trying to find other stuff. You need, simply put, the mass in kilograms, not in grams, in kilograms. You need the speed or velocity in meters per second, not kilometers per hour. So you need to get your units right to do the calculation correctly. What will that give you in terms of the unit for any energy, not just kinetic? Yeah, joules. So what do we get out of this? We get joules in terms of units. Joules is equal to kilograms times meters per second. Those are equivalent units. So 1 joule is equal to 1 kilogram meters per second. Then square this. Don't forget to square it. I almost forgot that. It's kilograms times meters per second, all squared. Okay, and then potential energy. What do you need to solve for that? Yeah, you need, good. You need the height. That's probably the most important variable. Height. Above ground, the vertical distance. That's what height is, the vertical distance measured from the ground. Usually it's the ground, directly upwards, perpendicular to the ground. And it's not in kilometers or centimeters, meters. This is just given. This is just going to be given to you. Put it in your formula sheet. Well, you can use 9.8. That's fine. Meters per second squared. Use the absolute value. This here is the mass, not in grams. That's a typical trick. It's not in grams. It's in kilograms. Okay. And what's the unit for potential any energy? Joules. So what do we have? This is all equal. So we have joules is equal to kilograms times meters per second squared times meters, which is just same as above. Kilograms times meters squared per second squared. That's just the same thing as meters per second all squared. Same thing. What about work? I'll throw this one in. I didn't have this as a question, but what do you need to calculate work? Actually, I did throw it in, but later on, but I'll do it now. It actually makes more sense to do it now. What do you need to calculate work? There's more to this than you think. So that's work. Work is the same unit as energy, joules. What do you need to calculate it? You want to put this in your formula sheet, right? I'm going to add this in. I'm going to add these two little railroad tracks. That means parallel. The parallel force times distance. Parallel to what? This is the force parallel to the direction you move. Okay. So whether sideways or upwards, you can't, for example, you can't be, got a book here, I'm exerting a force upwards with my hand. The force that my hand exerts, if this book is, let's say, moving to the right, the force that I'm applying by my hand is upwards. It's not parallel, perpendicular. There's no work done by my hand in this direction if the book is moving this way. It has to be parallel. I have to be dragging it along the surface for there to be work. Let's just go over the units first, and then I'll come back to that. So this is force, and it's in newtons. And this is distance in meters. Okay, so what do we get in terms of, and these are all equal, we get joules is equal to newtons times meters. That's another equivalent unit. You have to be familiar with the equivalent units. 1 joule is equal to 1 newton times meters. If you don't move, is work done? No, you have to move. Not only does the force have to be parallel to the direction you're moving, can't be perpendicular, it has to be parallel. But you also have to move. D cannot be 0. If D is 0, work is 0. If you don't move, work is 0. So you have to move in order to do work. If you lift something, what's the work done when lifting? This is a side note. Work done when lifting. The work done, when you're lifting, you're assuming you're lifting at a constant speed. So when you're lifting at a constant speed, what are you overcoming? What's acting down? Gravity's acting down. To lift upwards, you have to apply a force that's equal to Fg. If you're moving at a constant speed, that's what we're going to assume. Whether it's up a flight of stairs, up a ramp, or directly pushing an object up, you're applying a force that's equal to the weight, Fg. Okay? And usually for the vertical distance, we use h. This is always, when we're talking about lifting an object, this is the vertical distance upwards, perpendicular to the ground. Okay? So if you're moving up a set of stairs, it doesn't matter whether you're moving at a diagonal. We're only interested in the vertical height. What's the height of the stairs when calculating the work to reach the top? What's Fg? That's abbreviated. Yeah. So the work when lifting something, whether it's directly up or even up a ramp or up a stairwell, it's just mgh, where h is the vertical height of the set of stairs. It's the same, yeah. That's why when you're lifting something at a constant speed, the work you do goes into increasing its potential. The more work you do when lifting, the more potential it has at the top, because you've lifted it a greater distance. Okay, so I already covered that. My next question was going to be, one sec here. What's the equivalent units of joules and watts? Well, I already went over that, but I'll write it for you again. Watts. Can't get that A right. So joules, I'll write in red. We already did it above, so I'm just reminding you what we did. So there's two versions. There's this, 1 joule is equal to 1. You go back to the kinetic energy, it's, 1 kilogram meters per second. You can square the whole thing. If you're looking at the work, which is also measured in joules, it's just newtons times meters. Next question. What does rate of change mean mathematically? I mentioned this before. We're almost at the end here. I'm going to go back over, I think, some of the circuit stuff in 218, 217. What does rate of change mean mathematically? The rate of change of velocity, the rate of change of displacement, the rate of change of displacement is this. The rate of change of velocity is this. The rate of change of momentum is this. What am I doing in all three cases? Yeah, divided by time. Change in time or time. Usually initial time is 0, so it's just time. Yeah. The rate of change is how quickly something happens. Changes. When you're talking about how quick something happens or occurs, it's dividing by time mathematically. Okay, state Kirchhoff's laws. Yes, you need to know them. I'll write them down for you in a second. What are Kirchhoff's laws? There are two rules or laws. One regarding voltage, one regarding current. I'll go over the current one first because it's most current. No? Not funny? Okay, I tried. Okay, I'll draw a circuit. This is really the best way to explain it visually. This is about it. I'm going to go over the law regarding currents called the junction rule. Junction rule. So here's your junction. Junction is just a split. One wire turns into 2 or 3 or 4. Comes from railway or railroad junctions where the one railroad track will split into 2. You have 2 options. There's something that controls which way you go. But in this case, when you have current coming out of the battery, it comes to the junction. This is conventional current, right? Conventional current comes from the positive terminal into the negative. So anyways, the current's coming out of the battery and it reaches this green junction. It will split into 2 pieces, you could say. 2 portions. So this is called the junction rule. What does it say? It says the current going into the junction, which is I, is equal to the sum of the currents coming out of the junction. So in this special case, that's the equation for this specific junction, the green junction. Could it be different? Yeah, you could split into 3 instead of 2 or more. So you'd have an extra term if it was 3. Yeah, you want me to write it out? The current going into a junction equals, right, equals the sum of the current coming out. The sum That's the sum there. That's why I put that positive there. To sum means to add up. That's the first rule. Second rule, or law. I'm going to make use of the same circuit. Make it bigger though, helps me. I need a different color. I need to make it bigger. Sure. Start on the positive terminal. We're going to start there. We're going to come back to it, but this is where we're going to start because that's the positive terminal. We've got to include some things here before I show you the path. This voltage of the battery, I'm going to call VB. That's a supplied voltage. Think of it in terms of energy given by the battery. This is resistor 1. The one on the left is resistor 1. And this is resistor 2. The voltage that's used up across resistor 1 is V1. It's an energy. Think of it as it's actually the amount of energy per coulomb, but in simple terms, it's energy. The energy that's used up by the resistor or dissipated by the resistor we'll call V1. Similarly, by 2 is V2. What's it dissipated? What's this energy, by the way, dissipated into? Heat. If it's a resistor like it's been drawn there, it's heat. That's what a pure resistor looks like. Squiggly line. And the job of a pure resistor is just to dissipate the energy into heat. Okay, so why is it important that I indicate or label these voltages? Because the loop rule, this is called the loop rule, Kirchhoff's loop rule, says the voltage supplied by the battery equals the sum of the voltage around any loop. I'll show you in the diagram what I mean by that. The sum of the voltage around any loop. And I need to actually make that diagram just a little more complicated. Voltage around any loop. Usually it's a rectangular loop. Not always, but... Okay, so I'm going to make this diagram just a little more difficult so that it makes a little more sense. I'm just going to add on, sorry about that, but when you're drawing these diagrams, use pencils. I'm going to add another resistor here. I'm going to call this V. This is 3, resistor 3, and the voltage, usually we indicate it like this. Put a little circle around it. And we put a line here, a line there. This represents a voltmeter that you'd set up on either side of the resistor. Okay, I didn't want to draw it because for the others it gets too many things to draw. But anyways, visually, what does this loop rule mean? Well, I'm going to draw the physical loop first. It starts at the positive terminal. This is not really. I want some other color. None of these are going to work. Let me see. This might work. Okay, start here. Whoa, that's too thick. Be patient with me. Okay, start here. That's the positive terminal. So this is how you're going to figure out what all of this means. You have to actually, you don't have to physically trace it out, but at least trace it out in your mind. You're going to trace out one of two loops. Whoa, what's that? Okay. You're going to trace out either this loop that's one loop. And that's you can call loop 1. Or you're going to trace out this loop. Take your choice. Two different loops. Two different paths. Let's look at the first one. So the first loop is this one that I drew. It's a smaller loop, or passes through the first resistor as opposed to the second one. That's the loop. What about the loop? Well, we know that the loop rule says that the voltage coming out, this is now going to be expressed mathematically. The voltage coming out of the battery, which is a voltage that's supplied, it's an energy given, supplied by the battery, is equal to the sum of the voltages around any loop. What's the voltages around this first pink loop? V1 and V2, or excuse me, V3. What does it say? What does the loop rule say we have to do? It says here we have to take the sum. It has to be a sum, so we have to add them. Okay. So I'm going to make up numbers. Let's say this is 120 volts. Let's say this is 20 volts. Let's say we want to calculate or find V1. So VB is 120. V1, we don't know. V3, we know is 20. What's V1? V1 is just 100 volts. Thanks. Okay. That's the first loop. Okay. We just calculated what V1 is. I want you to do the same thing for the second loop. Shall I redraw the second loop? I can't. Second loop, I'll do, you know what? I'll redo it. I'll redo the second loop in deeper blue. Start here. Go farther. Include the second resistance. Come up with a new equation. Always starting with VB. Go around the loop. The equation on the right includes whatever voltages you come across traced out by the, in this case, the blue loop. V2 and what are the two voltages included in that blue loop? Bypass this one, it's not included in the blue loop. V2 and V3. So we have a new equation. The voltage of the battery is equal to V2 plus V3. Use the same numbers. Ask yourself the question, similar to what we did before. What's, in this case, instead of V1, what's V2? Plug in the numbers. Same numbers. Voltage of the battery is 120. V3 doesn't change. It's still 20 volts. It's the same circuit, so it's the same voltage. What's V2? Same as V1. That's an important point. You want to highlight that. Whoa. They're both 100. Same voltage. What do you know about these two resistors? They're side by side. What do we call that? Yeah. I just proved to you something I've been telling you in the past. Any resistors in parallel have the same voltage drop across them. So I'll just write it out. V1 is equal to V2 is equal to 100. What's so important about these? We just said it. They're in parallel. That's always true. And you can prove that using the loop rule. Kirchhoff's loop rule. Sorry, I'm going a little longer, but rate of change. What is needed for the work to be done? We just did last question. I can go over a bit of some of the circuits as well after this, but describe the energy change. I'm going to draw this. This is a side profile of a roller coaster. P&E. The roller coaster I would never get on again because the bar actually came loose. It did when I was with my Physics 11 class. It came loose. It's terrible. I'm not making it up. And the student that wanted me to go on it, she insisted, gotta go. Okay, I didn't want to go because I've been on it so many times. Okay, fine, whatever. And she was screaming her head off. So was I. Describe the energy changes. Describe the energy changes from A to B to C. In terms of, what do you think I mean by that? The energy changes. Which energy do you think? Yeah, good. In terms of potential and kinetic energy. And you can label them PEA, KEA, PEB, KEB, etc. Usually you start with, not always, but usually you start with no kinetic energy at A. Usually. Not always, but usually. So I'll write that down, but just keep in mind it's not always the case. But let's say KEA is 0. Okay, and I'm going to make up numbers. I'm going to use percentage. 100% here. Okay, B is close to, let's say B is near ground level, if not at ground level. So the coaster starts at A, and then it coasts down to B. How much potential do you have at B if you're practically at ground level? Yeah, so 0 potential. PEB is 0. KEB is 100%. I need more room. No, it doesn't work. I'll rewrite it. 100%. So what's happening? How would you describe that? What's happening to the kinetic and potential energy as you go from A to B? What's happening to your, one at a time, what's happening to your potential as you go from A to B? Going down, yeah, decreases. What about your kinetic as you go from A to B? Increases, yeah. So, as I've said before, as your potential goes down, your kinetic goes up by the same amount. And then C, I'm making numbers up. It's about the halfway point, 50%. Therefore, because it's halfway up to where you started from, it's 50% potential, and therefore 50% kinetic. What's happened to the kinetic energy as you went from B to C? Decreases. And what happened to the potential? Increases. Yeah, that's all I wanted. Mm-hmm. Let's see which is going to circuit one. Okay, just I can't give you every possible. I definitely go over some of the practice problems in the review package on circuits, but I'll give you some basic ideas for circuits. You had a question? Yeah. What? Yeah. When it goes, yes. Mm-hmm. The voltage is all used up. You can think of it as that. You start, let's say, with 120, and then by the time you get back to the battery pumps it back up to 120. Think of it as a water pump. It's like a water pump pumps it up to some height, and then it goes down, let's say, a waterfall. The energy is now zero, and the water pump pumps it back up so it's full potential again. That's probably the best analogy. So let's turn to, you should have your workbook here, page 217. I'm going to redraw this circuit, but I'm going to give you a general rule to remember. $120. What? Okay, so if you've got any sort of circuit, whether it looks like this or not, if it's got what looks like a whole jumble of resistors in it, and the question is, what's the current in the circuit? I'm going to draw the current. There's a current. What is the current in the circuit? In this case, it's actually here. It's the same thing. What is the current in the circuit? Usually, what is the current in the circuit? Usually, that will mean what's the current. Same thing as asking what's the current coming out of the battery. Same thing. They will usually place the ammeter somewhere. In this case, they placed it here. It could be placed here, could be placed here, here, here. Anywhere before the junctions. Okay, so if you get the question, what is the current in the circuit? It's another way of saying what's the current coming out of the battery. So here's your hint. You can jump right to this. What is the current coming out of the battery, or what's the current in the circuit? It's just the voltage of the battery divided by, we talked about this, the total resistance. You got to find the total resistance. How do you find the total resistance in this case? What would you do? Yeah, good. Start with the parallel. So that's the trick. If you have what looks like a jumble, an assortment of resistors, start with the parallel part and simplify. Turn these two into one. We did this already, so I'm just summarizing. Turn these two into one. One resistor now that's in series with this one. And then just add them up. And when you add them up, you get your R total. So go over, main point is, go over finding the total resistance for each of the different examples. Because once you've got the total resistance, you've got the current coming out of the battery. It's just VB over the R total. That's the point of finding the total. That's the point of finding the total resistance. Okay. Okay. So that was question 4 that I used as an example. Last one. Okay. I'm going to go over the main points of 5 because that will help you as well. If you get any question that asks you for, oh boy, it's getting low, voltage, in this one, voltage of the battery. But it could be the voltage across any resistor as well. What's the voltage? I would see, this is just the general, I would see, check to see whether there's any parallel resistors. And there is in this case. There's a 6 ohm and 12 ohm. They're in parallel. What do you know about this usually helps. There's no fast rules. You have to go over all the problems that I assigned you. But what do you know about resistors in parallel in terms of voltage? The voltage lost or used up across any resistors in parallel, in this case the 6 and the 12, is the same. The voltage across the 12 and the 6 is the same. Voltage. Okay, now look what I'm going to do here. I'm going to add this. This is I'm going to call this my I2. This is my I1. And they add up to give I. So if this is true, if the voltage across the 12 and the 6 is the same, how can I express that in terms of Ohm's law? What does Ohm's law say about the current? Voltage is equal to, V is equal to IR. Good. So, V is equal to IR. So what do we have for each of these resistors? I'll start with the one at the top, although the number is 2. I'll just write down I2 times 12. What about the one at the bottom? I could write I1, but I already know what the value is. In this case, it's 4 amps times 6. What do I know about these two terms, the I2 times 12 or the 4 times 6? They're equal, yeah, because they're equal to the voltage across the resistors. So 4 times 6, which is 24. I2 times 12. I2 must be 2. Okay, so let's replace this with, let's keep it simple. Forget about I1, I2. Let's replace this with 2. We got 2 amps above, 4 amps below. They come together at this junction. What does the junction rule say? Current going into the junction must be equal to the current coming out. So what is I equal to? Yeah, 2 plus 4. Or a 6. Okay. So now I know, let's replace this with what we know. This is no longer I, this is 2 amps. 2 amps. Going into the 8 ohm. The voltage across here we calculated. What is it? What's the voltage across the 6 ohm resistor? 6 times 4 or 24. We're going to come back to that. Okay. Now what am I interested in? I'm interested in the voltage of the battery. Let's draw a loop. We'll do that one. Thicker? I want a thick one. Draw a loop. Well, not that thick. Draw a loop. I call it a loop. It's just basically a pathway. Starts at the positive terminal, ends at the negative terminal. Almost done here. The voltage that's used by this 6 ohm resistor is 24. Okay? What's the voltage that's used by this 8 ohm resistor? If the current through it is 2. Yeah?
Or wouldn't the current be 6 if it's I1 plus I2?
Did I say? Oh, sorry. Thank you. I made a mistake here. It's 6. Okay, what's the voltage through the 8 ohm if the current through it is 6? This should be 6. How do you find voltage if you're given current and resistance? V is equal to IR. So the voltage loss across the 8 ohm is 6 times 8, 48. So we have the voltage lost across here is 24. Voltage that's lost across the 8 ohm is 48. How does that relate to the voltage of the battery? VB is equal to the voltage lost across the 6 ohm, which is 24, plus the voltage lost across the 8 ohm, which is 48, which works out to be 72. Okay, so I'll post this for you. I got it recorded for you, so I'll post it.